This video is about topic 4.3, which will be about vectors and vector equation of a line and the angles between those lines. So, first, a quick review. A vector is something that has both direction and distance traveled, or magnitude. It can be written as, in component form, x, y, z, where the top number represents movement along the x-axis, the middle, the y-axis, and the bottom, the z-axis. So, the first part of this lesson, 4.3.1, the vector equation of a line. The equation of a line can be described using vectors. This is the form. R equals A plus T times B. These two are vectors. So is this. Now we will break this apart by variable. The first we'll look at is A. A is the initial position vector. This would be a vector from the origin to any point on the line. Well, to find this, for example, you would take the point 7, 9, 3, and you would subtract the origin from it. You would go to this, you would subtract the x from x, y from y, and z from z. And you get, in component form, 7, 9, 3. The next variable we will look at is t. T is the scalar multiple of our next variable, b. B is the direction vector. This describes the direction of the line. Our last variable is r. R is the position vector of a new point on the line. To find r, first multiply the direction vector by the scalar, and then add the initial vector. Follow the order of operations. Okay, now we are ready for a practice problem. Line 1 has a point 4, 1, 3 and is described by vector in component form 2, 2, 2. First question, write the equation of line 1 in vector form. Second, determine whether the point 8, 5, 5 lies on the line. Problem 1, which is, write the equation of line 1 in vector form. So first, what do we need to know? This is the equation we're looking to fill out. What we'll need to know are these two vectors, these two variables that we do not know currently. Secondly, what do we know already? First thing that we know is that there's a point on the line with the coordinates 4, 1, 3. This gives us the initial position vector A. To find this, we will do what we talked about earlier, subtract the origin. X minus x, y minus y, z minus z. Gives you in component form 4, 1, 3. This is our variable A, our initial position vector. Second thing that we know is that the line is described by the vector 2, 2, 2. This is the direction vector B. No work required for this one. Okay, so we know that A in component form is 4, 1, 3, and B in component form is 2, 2, 2. We now know all our variables. We can do the next step, which is to plug our values into the equation for the final answer. And here you are. R equals in component form 4, 1, 3 plus T times in component form 2, 2, 2. Alright, problem 2, which is determine whether the point 8, 5, 5 lies on the line. So what do we need to know? We need to know if this vector 8, 5, 5 is a position vector on the line. We made this a vector the same way that we would find the initial position vector, where you subtract the origin from the point. Secondly, what do we know currently? We know the equation of the line, which we found the answer to problem 1. Okay. Our first step, substitute the vector in component form 855 for r and solve for t. When you substitute it in, this is what you get. The next step, rewrite the equation as 3 separate equations with x, y, and z coordinates together. And those are the 3 equations that you get. 8 equals 4 plus 2t. 5 equals 1 plus 2t. 5 equals 3 plus 2t. X, y, z. If this point does lie on the line, then t should be the same in each equation. So what we're going to do is we are going to solve each of those equations. The first one, 8 equals 4 plus 2t. Subtract 4 on each side. Divide by 2. 2 equals t. So this is what we're going to be looking for in the next 2 equations. So, on to the next one. 5 equals 1 plus 2t. Subtract 1 on both sides. Divide by 2. 2 equals t. So far, everything is working out. The third one. Subtract 3 on both sides. Divide by 2. 1 equals t. Because not all values for t are the same, 0.855 cannot be on line 1. And that's our answer for the next question, for the last question, question 2. Okay. We are now moving on to chapter 4.3.2. The angle between 2 lines. This is the same concept as the angle between 2 vectors and has the same formula, except the angle between 2 lines takes the absolute value of the dot product between vector b1 and vector b2. We do this because lines continue infinitely. Their intersection forms both an acute and obtuse angle. We only care about the acute angle. So in order to find that acute angle, we need to take the absolute value of the dot product. We are now ready for a practice problem. Yay! So, first question. Find the angle between the lines. Line 1, x equals 2 minus 3t, y equals negative 1 plus t, and line 2, x equals 1 plus 2s, and y equals negative 4 plus 3s. First, rewrite these 2 equations in component form. So line 1 equals 2 in component form, 2 negative 1, 2 negative 1, plus t times in component form, negative 3, 1. Negative 3, 1. Line 2, we're going to do the exact same thing. In component form, 1, negative 4, 1, negative 4, plus t times 2, negative 3. 2, 3. 2, 3. These 2 vectors become vector b1 and vector b2. These 2, the direction vectors, are the only vectors that we care about in this problem. We are going to take these 2 vectors and substitute them into our equation. So where b1 was, this vector will go. Where b2 was, this vector will go. And this is what we get. This equals the cosine of theta. Okay. Now then, we're ready to evaluate. I like to break this up into 3 chunks. I solve the dot product, and then the magnitude of one vector and the magnitude of the other. So first, find the dot product of in component form negative 3, 1 and in component form 2, 3. So just like dot product, we multiply the x coordinates and then we add it to the multiplied y. 6 plus 3, negative 6 plus 3, negative 3. Okay, now let's find the magnitude of our first vector, vector b1, in component form negative 3, 1. You square each of the components, so negative 3 squared plus 1 squared. 9 plus 1, square root of 10. That's as far as we can go. Now we'll find the magnitude of our second vector, vector b2. In component form, 2, 3. So 2 squared plus 3 squared, 4 plus 9, combine those, 13. Square root of 13. We're going to take these values and we're going to be putting them back into the equation, just like this. Now we will continue to simplify. So first, take the absolute value of negative 3, combine these two radical expressions, and you get 130, the square root of 130. This is as far as you can go after you take the inverse cosine on both sides without your calculator. But let's assume this was on the calculator portion, so you can use your calculator to figure out what the inverse cosine of 3 over the square root of 130 is. And if you did, you would get 1.30 radians. You'll have to have 3 sig figs because this was an irrational number. Okay, that is it for this lesson. So now, of course, we are ready for homework. Okay, these are all IB questions as well. So, first one. Second. Third. And once you're ready, here are the answers. Thank you for watching. I hope this helps you with your final.